All right, so we've opened up this interactive Python notebook. So what is this? What is Jupyter Notebook, right? So just looking at this, you're probably noticing a few things. First off, you can see there's just like text or markdown here. So this is just like actual text. And then there's code. But the interesting thing about the code is that the code is segmented into cells. So this is different from if you have a .py file where you just have like a bunch of code and a bunch of comments. You know, it's not segmented, it's just a single file. If you want to run the file, you have to either run the entire file or just not run it at all. And so that's the thing that's really interesting and useful about Jupyter Notebook is that it allows you to run code one cell at a time, or it allows you to run portions of your notebook without running the entire thing. And so that's actually really useful for data science because it allows you to, for instance, import a really large data set and then make changes to the data set or manipulate the data later on without having to reload the data every time. So that's one of the reasons Jupyter is really useful, especially for data science. And yeah, so you might also be wondering, okay, why is it called Jupyter? That's a really random name. So if we toggle it again, you can see, oh, the way it's spelled. Oh, what's interesting about the way it's spelled? So it's P-Y, right? Like Python. Yeah, so it's actually called Jupyter because it supports 3 languages, Julia, Python, and R. So that's why it's called Jupyter. Pretty neat little bit trivia right there. So yeah, that's Jupyter Notebook. The last thing I wanted to talk about is just how to use it. So in Jupyter, there are actually 2 modes. There's an overview mode and there's an edit mode. So you can see right now we're in the overview mode because this line right here is blue, right? So if the line is blue, then you can use the arrow keys to go around to different cells. So this is the overview mode. And so if you want to actually edit a cell, all you have to do is hit return. And then you can see this line turns green and the cursor starts blinking. So this allows you to actually write some code. And then if you want to go back to the overview mode, you can just hit escape and it's going to turn blue again. So so those are the 2 modes that makes it easy to navigate the notebook. Now, if you actually want to run a cell, you can hit run up here, or you can hit command return, command enter. And so you can see when we do that, it takes these empty brackets and puts a 1 in the empty brackets. So what that means is that this is the first cell to have run. And so if we do that again, and we run the second cell, we can see it fills it in with the number 2. So this is the second cell to have been run. And so that's really important. And I'd say this is like pretty much the only downside of using Jupyter is that you have to be careful of the order in which you run cells. Because if you run cells in the wrong order, you could get like a kind of tricky logic error where you didn't expect like some variable's value to take a value or to take a specific value because you ran it out of order. And if that ever happens when you're following along here, you can just go to kernel and restart and clear output. So that's just going to restart the notebook and basically forget about everything that has been run. So again, if that ever happens, just kernel, restart, and clear output. All right. So all that was just an introduction to Anaconda, an introduction to Jupyter. So now I'm actually going to be talking about the problem we're going to solve here, what we're actually going to be doing. So here you can see, okay, we do data equals read CSV and then the CSV file and then data.head. It's going to show us the first 5 data points in this file. So what is this file? So this is a university admittance data set. So this is for a fictitious, fictitious, is it fictitious or? Yeah, just like a fictional university. This is synthetic data. So let's say there's some university where students have to take 2 exams in order to get admitted into this university. And so you can see this first student right here at index 0, they got a 34 on the first exam, 78 on the second. They were not admitted. Okay, that makes sense. They did pretty badly on the first exam. This last student here at index 4 got a 79 and a 75, and they were admitted. Okay, that also kind of makes sense. It seems like they did like decently well in both exams. So we're going to use machine learning to predict admittance from exam score. And so this is actually a very simple problem. It's a problem where you wouldn't necessarily need to use machine learning, but the reason we're doing it here is to illustrate how these algorithms work. And that's going to make sense in a little later. Excuse me. That's going to make sense in a little bit when we start to create some visualizations. All right, so next we're going to go to this next cell. And so this next cell basically sets up the data nicely so that we have the exam scores in a matrix called X and the admittance data in a vector called Y. And so we're going to run that. And then we're going to define this plot data function. And again, to run a cell, it's just command enter, or you can hit run up here. And so finally, we're going to call this plot data function. And so we can see that this is another way to visualize the data. So we've got the data looking like this up here, right? And so here we've got exam 1, exam 2 admitted. Here on the x-axis, we've got exam 1, y-axis, exam 2, and then admittance is color coded. So green, these are the students who were admitted. Red, these are the students who were not. And so this kind of makes sense because you can see in this top right quadrant, students who did pretty well in both exams are in this top right quadrant, and they're all green, right? And students in this bottom left quadrant did pretty poorly on both exams, so they're red. I guess the only kind of non-trivial thing to note about this is some students did really well on one exam, like these 2 points, or these 2 points, but they did really poorly on the other. So it seems like it's not enough to do well on only one exam. You have to do decently well on both. All right, so that was all just setting up a problem. So here's a question for all of you. You can use the chat to answer this question. So do you see any obvious kind of boundary between these two classes, or any kind of like simple way that you could separate the two classes, either like a visual boundary or like some kind of rule, some like quantitative rule that you could give to separate these two classes? Again, is there like an easy way that you can just like see to separate the two classes? Any ideas? Oh, okay, we got someone in the Q&A. Okay, y equals minus x. Yeah, just about. Yes, that's a really good. Oh yeah, plus 100. Okay, yeah. So that would be a line over here, and then like that, right? Yeah, so that's a really good answer. Someone else said looks like a decaying exponential function. Yeah, so those are both really good answers. And so the example with the line like this, yeah. So drawing a line, that's really good. So actually drawing a line that corresponds to basically taking a weighted average, and we're going to show that later. We're actually going to show an algorithm that does draw a line to separate the two classes. But it's going to do that in an automated way, so that we don't have to just look at the data and say, okay, we want to draw a line. And we're also going to see an algorithm that draws a curve, but it draws the curve using a very interesting technique by transforming the data. I think there's another answer here. Let's see. Okay, linear regression. Yeah. So we're actually going to talk about linear, or yeah. So that's interesting. You mentioned linear regression. We're actually going to talk about logistic regression here. So linear regression is when you want to draw the line of best fit. Here, we're basically looking for the line of best separation, right? All right, so those are all really good answers. And I asked that question basically to try to motivate the use of machine learning. So here, right, this data set's really simple. It's only two-dimensional. All right, what library? Oh, so we're gonna be using scikit-learn. I'm gonna get to all the details just a little later on. All right, so again, so the reason I asked this question is to kind of motivate machine learning. So here, this data set, really simple, only two features, exam 1, exam 2. It's two-dimensional. We can plot it like this, and we can just look at it and be like, okay, well, there's a clear trend. So imagine, for example, if we had exam 1, exam 2, and also undergraduate GPA, or for example, like letters of recommendation, like the strength of the letters of recommendation. Imagine if we had 4 features or more. This could be like 4-dimensional or even a higher dimensional, where it's not as easy to just look at the data and be like, okay, well, it's clear there's some line or some curve that should fit the data very well. So that's one point. If the data is higher dimensional, it's not as easy to just look at it and determine what the best line or curve is. And in addition to that, here we only have 100 data points. In many instances, you could have 1,000 data points, millions of data points, and a lot of machine learning, or specifically deep learning applications, having billions of data points is pretty common. And so if you have that much data, it's going to be hard to just look at it and determine what like the line of best fit or like the curve of best fit is going to be. And so basically machine learning automates that whole process. So instead of looking at the data and saying, okay, I would draw like this line, the machine learning algorithm basically just finds the best line to draw. And so, yes, all that's just like motivation for what we're going to be doing next. But those were all good answers that you gave in the chat and the Q&A. All right, so after that, we're going to define this decision boundary function, and then we're actually going to get into it with making some machine learning classifiers. So thank you all for bearing with me up to this point. This is the part where it starts to get pretty cool. All of that was just like set up and kind of motivation. So the first classifier, the first machine learning algorithm classifier that we're going to be creating is called k-nearest neighbors. And it's actually super simple. It's pretty much exactly what it sounds like. And I'm going to get into what that means after writing the code. So in each of these cells, we're going to create a different classifier. And the format for all these cells is going to be the same. So we're going to start by importing the classifier from this package called scikit-learn, which comes with Anaconda. So this is why you need Anaconda to actually follow along. So we're going to do import, or actually we're going to do from sklearn.neighbors. And I would encourage you to like do tab autocomplete for a lot of this stuff, because like with any IDE, tab autocomplete is really helpful. So from sklearn.neighbors import, and then we're going to say k-neighbors classifier with a capital K and a capital N. Let's see. Okay, yeah, made my screen just a little bit bigger. Actually, that might be too big with cutting off the bottom. All right, so import k-neighbors classifier. And so next we're going to create an instance of it. KNN is what I'm going to call it. And I'm going to say k-neighbors classifier. Then I'm going to throw some parentheses on the end because we're making an instance of this class. And so now I'm going to go ahead and run it. You don't have to run it at this point, but I'm going to. And the reason I'm going to is because now I can put my cursor inside the parentheses and then hit Shift Tab. And that's actually going to pull up all the arguments for this class. And so you can see that the first argument is the number of neighbors, and the default is 5. So I'm just going to copy and paste that to be explicitly clear. So next I'm going to do knn.fit and then capital X lowercase y. So again, this capital X corresponds to the matrix of exam scores. It's a matrix because it's two-dimensional. So every row corresponds to a student and every column corresponds to exam 1 and then exam 2. And y, it's lowercase because it's a vector corresponding to the admittance decisions, those ones and zeros that we saw above. So finally, I'm going to call this decision boundary function on knn. All right, and so now I'm going to run it. And oh, check that out. That looks pretty neat, huh? Yeah. So this is what the decision boundary looks like. So this, okay, I should take a step back. So this might not be obvious what's happening here. So this light green region corresponds to all the points that the classifier predicts as being admitted. So for example, like this guy right here corresponds to a student who got like an 80 on the first exam, 60 on the second exam, corresponds to the classifier thinking that this student got admitted. And the light pink, it's the same, except for students that the classifier predicts as having been denied. All right, so I haven't actually explained what k-nearest neighbors is, aside from saying that it's what its name implies. So how does k-nearest neighbors work? Well, to make a prediction on a new point, for instance, this point right here, we're on exam 1, 40, exam 2, 80, it looks at the k nearest neighbors. So in this case, there are 5 nearest neighbors because we set it equal to 5. So it looks at the k nearest neighbors. It says, okay, there's 1, 2, 3, 4, 5. I'd say those 5 points right here are the 5 nearest neighbors. And it says that, okay, here, 4 out of the 5 nearest neighbors are red, and 1 out of the 5 nearest neighbors is green. So since the majority is red, it predicts denied. And so that's really all it is. It just looks at the k nearest neighbors and chooses the majority class to make a prediction. All right, so we got some questions here. Oh, damn, that's pretty cool. Someone wrote a blog post about this. So that's pretty neat. Yeah, so check that out if you're interested in more details about it. So in this workshop, I'm not going to go super in depth with all these algorithms. I'm just going to give you a brief overview and just talk a little bit about the process of making predictions and kind of tuning some of these parameters, or specifically hyperparameters here. All right, so this is when the number of neighbors is equal to 5. What about if we bump the number of neighbors down to 1? Any ideas if the decision boundary is going to look smoother or more jagged? And any ideas if we move it down? All right, so we got some answers in the chat. Just one sec. Check that. All right. Yeah. So okay. So if someone says oh, actually someone says error that decision boundary is not defined. Oh yeah. So if you get the error that the decision boundary function is not defined, just make sure to run this cell up top. All right. All right. And so now, so to answer this question, so some people are saying, okay, jagged. Someone's saying it'll look smoother. Oh, also, when someone asks, can you send that link to everyone? That link is in the Q&A. Okay, so some people are saying more smooth, some people are saying more jagged. So right now it's at 5. If we bump it down to 1 and run it. All right, so this is what it looks like. So in my opinion, it looks a little more jagged, especially because at this point, some of this stuff down here looks more jagged than it was 5. Than when it was 5. All right. Someone raised their hand. Wait, yeah. I apologize. I'm not sure if someone raised their hand. If you have a question or anything, I'd encourage you to put it either in the Q&A or in the chat. Oh, we can't see the link. Okay, my bad. All right, so I'll include the link here. All right, so there it is. Okay, cool. All right, yeah. So I'm thinking that it looks more jagged. So you might disagree with me, or you might forget what it looks like when it was 5. So what if we bump it all the way up? What if we make it more extreme and bump it up to 25? What's that going to look like? Any ideas? More smooth or more jagged? All right, someone's saying way more smooth, way more smooth. Okay, cool. So if we do that and then run it, okay, yeah. So we can see it looks a lot more smooth. It almost looks like a line, right? And so you might be wondering, okay, why is that? Well, the explanation is actually pretty intuitive. Basically, when the number of neighbors is something very low, like 1, the decision boundary is basically going to be perturbed by points right between the two classes. It's going to be completely determined by points like right between the two classes. Whereas if we bump the number of neighbors up to something like 25, it's going to take many more points to determine what this decision boundary is. So it's not going to be as perturbed, or it's not going to be as jagged based on points right between the two classes. All right, so that's k nearest neighbors, pretty straightforward. Like I said, I'm not going to go into a ton of detail with k nearest neighbors, just like a pretty high level overview for all of these algorithms. So someone's asking, is it not good to have a higher number of neighbors? So that's actually a very interesting question. That actually depends based on your data set and the type of fit you're trying to achieve. So I actually wasn't going to spend a ton of time talking about this, but with machine learning, there's a general kind of problem you're trying to solve, or a general set of like competing objectives where you want to fit your data set well, but you also don't want to fit it too well such that it memorizes your data set and doesn't generalize to new examples. So determining the number of nearest neighbors, you probably want a number of neighbors in between something like 1 and something like 25 to try to meet those two conflicting objectives. And like I said, I'm not going to spend a ton of time talking about that right now. Yeah. So that has to do with like creating a train test split in your data set to first train your algorithm and then test how well your algorithm does, or to validate how well your algorithm does. Here we're only going to be looking at like one data set, which is the train set. So again, this is just to illustrate how these algorithms work, not necessarily to talk about how you would do it like in the real world. Again, this is like a very simple data set. All right, so that's k nearest neighbors. Next, I'm going to talk about something called logistic regression. So up top, when I asked the question about, okay, how would you do this without machine learning? A lot of people added really good answers about drawing a line or drawing a curve. So logistic regression is simply going to draw a line between these two classes. So I'm going to write the code first, then explain it. So we can say from sklearn dot linear model, and then I'm going to say import, and now logistic regression. All right, so we're going to take that, and then I'm going to create an instance of it called log_reg equals logistic regression. Now throw the parentheses on the end. Make sure to do that. And then log reg dot fit capital X lowercase y. Remember, X is a vector, or excuse me, X is a matrix, so it should be capital. Y is a vector, it should be lowercase. That's just the standard mathematical notation. And then finally, decision boundary log reg. Okay, so with all that, we're going to run it. And so we can see it draws a nice line. Okay, cool. So it draws a line. That's what I said. That's what we're expecting. You know, it is in the linear model package. So this is great. This is what we're expecting. But then this brings up, yeah, yes, X is a matrix. That's correct. So yeah. So this is cool. But then it brings up a pretty interesting question, or a question that turns out to be pretty fundamental to machine learning, which is how does it know what line to draw? Right? Like this line seems like a pretty good fit for the data, but why did it draw this line versus like another line, right? Like there are an infinite number of possible lines it could have drawn. Why did it choose this one? And so this goes back to the fundamental question in machine learning, which is how do algorithms actually learn from data? How do they know which predictions to make? And so to answer this question, I'm going to be talking about something called gradient descent. So basically, in general, machine learning algorithms construct an error function, which basically tells you how bad the model is, how incorrect the model is, how inaccurate the model is. And so then it simply minimizes that error function with respect to the model's parameters. So in this case, we can see we're doing linear regression. This is not related to the exam data set, just to put that out there. So here we're doing linear regression. This line is parameterized by m, which is the slope, and b, which is the y-intercept, right? Y equals mx plus b. You probably learned that like way back in middle school. All right, so we're trying to find the best m and the b for the these points here. So we construct this error function, and then we minimize this error function. So I'm going to explain something called gradient descent, which is a general method to optimize a function or to minimize a function. So there are many ways to minimize a function. So I guess the most common way you're probably familiar with is in calculus. You can just take the derivative and set it equal to 0, and then solve for the parameters. So that's one way to do it. But oftentimes this error function is going to be more complex, or excuse me, more complicated. I shouldn't use complex because that gets into the square root of -1 and I and everything. But yeah. So oftentimes the error function is more complicated. So it's not as simple as using the closed form solution that you probably learned about in calculus. So I'm going to be talking about gradient descent because it's very commonly used in machine learning, and it's going to come up also later in this workshop as well. So gradient descent, if you've taken Math 230 or Math 231, you know that the gradient is the derivative of a higher dimensional function. And the gradient actually points in the direction of steepest increase. So if you want to go to the bottom of the function, if you want to minimize the function, then you want to go in the direction of steepest decrease, which is the direction of the negative gradient. So you basically take the gradient, update these parameters, update m and b in the direction of the negative gradient, and then repeat. So all that might sound kind of complicated, but really you could just think of it as taking steps downhill on the cost function. And so that's what gradient descent does. Here with linear regression, you can see how it's applied, how the line is adjusted when you take these steps. And so again, gradient descent is just one method for minimizing a function. There are many ways to do it. I think logistic regression actually uses a method called Newton's method, which is just a root finding method. So gradient descent is not the only way to do it. It's not actually the way logistic regression does it. But I just want to talk about it because it's very general. And this kind of gets to the essence of what it means for an algorithm to actually learn from data. All right, so that's logistic regression. All right, so looking at the line, some people mentioned this when I asked the question about this up top about, okay, well, so a line might be good, but you know, maybe a curve might be even better. So that's what we can do. We can also draw a curve. And you can see how a curve might be better just by looking at the line here, right? Like these guys are excluded, or these guys are wrong. These green guys, it gets those wrong too. So maybe a curve would be better. So we're going to use a support vector machine to draw a curve. And so a support vector machine is very interesting because it's actually a linear model, but it first transforms the data into a higher dimensional space and then applies this linear model. So again, I'm going to write the code first and then explain it. So first I'm going to say from sklearn.svm. So import, and now svc, because we're doing classification, support vector classifier. And so next we're going to create an instance of it called svm. svm equals svc. And now I'm going to go ahead and run it. And so I'm going to run it in order to get inside the parentheses and check out the parameters. So there are two parameters we're going to be using, kernel and degree here. And so these specify the transformation of the original data. So I'm going to do kernel equals poly and degree equals 2. All right. And so next I'm going to say svm.fit capital X lowercase y, and finally decision boundary svm. All right. So I'm going to explain what these two do in just a second. I'll check the Q&A first. Oh no, it's chat. 1 second. Okay, how to get the value inside the parentheses? Oh yeah, so first you got to make sure that you run this line right here, and then once you're here, you hit Shift and Tab, and then it's going to show you the parameters. So again, it's important to run this first in order to check out the parameters, because this basically says, okay, so we want to get this package, or we want to get this class from Anaconda. So it brings it in, and then it allows you to actually look at it. All right, so back to the SVM. So we can see it draws a pretty nice curve. So you might be wondering, okay, what does this kernel mean? What does this degree mean? Or you might have already kind of guessed at it. So this transforms the data using a polynomial of degree 2. So it basically just squares the data. It's like a little more complicated than that. So it squares the data, but like I said, the SVM is still a linear model. So that might seem like really counterintuitive or really confusing, right? Like this doesn't look like a line at all. This is clearly a curve. This is clearly non-linear. So what do I mean when I say that the SVM is a linear model? Well, I mean that it's a linear model with respect to the transformed data, with respect to the data transformed as specified right here. And so that still might be kind of unclear, might not make a lot of sense. So to kind of explain it better, I'm going to pull up this image. So this is not related to the exam dataset. This is just a synthetic dataset to illustrate. Here we've got these two features, x1, x2, and we've got these two classes, red and blue. So here you can see there's no line that you can draw that's going to separate the red from the blue. But if we transform this data, if we put it into a higher dimensional space, as here on the right, you can see that, okay, now we can draw a line, or to be like technically correct, we can draw a plane, right? Since it's in 3 dimensions. So if we take the original data that's not linearly separable and transform it in some way, it becomes linearly separable. And then we draw the plane, and then we create the linear model. And then when we project it back down, it's going to look like a circle or potentially an ellipse. And so the exact same thing is actually happening right here. All right, so here's another question. So if we change the degree to 1, what is it going to look like? Any ideas? All right, a straight line like the previous one. Yeah, exactly. So if we do that, yeah. So we can see this should look almost identical to the one up top. Yeah, and so it is. All right, so that's cool. But now here's another interesting question. If we do degree 3, what is it going to look like? Right, like in general, a degree 3 curve is pretty different from like a degree 2 curve. So if we do that, I'm just going to do it. So we do it. Okay, we see it looks pretty nice, but how different is it from degree 2? Okay, it looks more or less the same as degree 2. What about like degree 4? Okay, it looks more or less the same. All right, so it's the same. Yeah, exactly. Yeah, and so why is that? Why is it the same? So the reason why it's the same is because when we do degree 3 or when we do degree 4, it actually saves all the lower degree terms. So it saves the degree 1 term, saves the degree 2 term, so on when we do like degree 4 or degree 5. And so the model's actually smart enough to realize that, okay, here with degree 2, it gets everything right. Like you can't make the model better than this, just in terms of like misclassification rate, right? Like there's no green and red, and there's no red and green. And so the model can set the coefficient for the higher degree terms to 0 or pretty close to 0 when we do something like degree 5. So again, the model is basically smart enough to figure out that degree 2 is good enough. And so you won't see big changes after degree 2. So that's an SVM. All right, so far we've talked about something that's like pretty intuitive, k-nearest neighbors, something that you might expect, or that some of you did guess to do, just draw a line. And then we said, okay, well, maybe a line's not the best fit. What if we draw a curve? And so next we're going to talk about something that the decision boundary looks very different from the ones above. And the decision boundary might seem kind of crazy, but it turns out that the way the decision boundary is constructed actually has to do with a way that a person might approach this problem, or a pretty intuitive way of just like thinking about this problem or this general class of problems. And so this algorithm is called a decision tree. And so we're going to talk about this next. And so yet again, I'm going to write the code first, then show you the decision boundary, then explain what it actually does. So decision tree. So we're going to say from sklearn.tree import. And so I'm going to say, yeah, actually, what is it? Yeah, decision tree classifier. Next, I'm going to create an instance of it. Tree equals decision tree classifier, and then throw some parentheses on the end. And finally, or not finally, tree dot fit capital X lowercase y, and then finally decision boundary tree. All right, so make sure you got all that. All right, so that should be good. So now we're going to run it. And whoa, check that out. Bet you weren't expecting that. Whoa, unless you already know a lot about machine learning, in which case this is an introductory workshop. But anyway, all right. So this is what the boundary looks like. Looks pretty spicy, I would say, pretty spicy hot. So yeah, so what is this? What's going on here? Like how do decision trees work? Like I haven't explained that at all. So decision trees, it turns out, they're a very inquisitive algorithm. So what do I mean by that? Well, decision trees ask a lot of questions about the data. And it turns out that every line here, every vertical or horizontal line, corresponds to a single question being asked about the data. So for example, this line corresponds to the question of, is exam 1 score less than or equal to, what is it, like 38 maybe? So it's asking, okay, is exam 1 score less than or equal to 38? And if it's less, then it says, okay, I'm going to predict denied. If it says greater, it says, okay, well, I'm going to ask some follow-up questions, and so on. Or potentially other questions were asked before this question was asked, leading to this area right here. And so it turns out we can actually visualize what the tree looks like. So I've got this cell right here. So this cell is going to run for me because I have this graphics package installed. If you don't have the graphics package installed, this next cell shouldn't work for you. That's okay. You can just install it after the workshop. Actually, I'm gonna check. Someone asked a question. Could you explain something about random forest, please? Oh yeah. So data is not classified using. Okay, so first someone asked, could you explain something about random forest? And so here we're talking about a decision tree. There's actually something else called a random forest, which is a collection of decision trees. And so it's a collection of decision trees, I believe, where each decision tree only has access to a portion of the data or a portion of the features. And so that actually improves predictive power if you have a collection of classifiers. That's a very general method called ensemble methods. And actually, I can just show you where it is. If you do from sklearn.ensemble, you can do import random forest classifier. And so ensemble just means it's a collection of classifiers that are used together to improve predictive power. And so again, random forest is a collection of decision trees, and each tree is trained on a different subset of the data, or a possibly overlapping subset of the data, and a possibly overlapping subset of the features of the data. All right, and so then someone else asked, data is not classified is using a decision tree wise, then is this regression tree? In this case, we are doing classification because we're predicting like two classes, right? Like admitted or denied. You can also use decision trees for regression. I'm not sure if I'm really understanding that second question, or if that's if that's like, if that answers the question. All right, so next, so I can run the cell. The cell might not work for you unless you have Python graph is involved, or excuse me, installed. So we can actually see this decision tree, and I'm going to zoom out for a second to yeah, to see all of it. So it's kind of a big tree. So you can see the first question that's being asked is exam one score less than or equal to 56.7? So if we go up, we can see, okay, exam one, 56.7, that's over here, right? So that's this question. And then we can see exam two less than or equal to 83, right? So exam two, 83, yeah, so that's this guy. So we can see there's a one-to-one correspondence between this diagram and the decision boundary. And so what's happening here is that all of these nodes are questions, except for these nodes at the bottom, right? These nodes at the bottom are decisions. These are like the answers to the questions. Like, oh, okay, like if so on the left is true, on the right is false. So if the answer to this question is true, it predicts denied. If it's false, then it's going to ask like this follow-up question. So that's how the decision tree works in terms of structure. But I haven't actually explained how the decision tree works in terms of like knowing which questions to ask, right? So this is a similar kind of question as up top with logistic regression, right? It draws a line, but how does it know to draw that line? With decision trees, okay, it draws a bunch of lines, but how does it know to draw these lines? Or more informally, how does it know which questions to ask about the data, right? So decision trees actually use a criteria called impurity. And impurity basically measures the amount of green in red and the amount of red in green. And it seeks to minimize the impurity. So if you think about it, again, kind of informally, minimizing impurity is like the same as maximizing purity, or like keeping the red in red and keeping the green in green, which is ultimately what we're trying to do. So at every step, the decision tree exhaustively looks through all the potential splits it could make and chooses the one with the lowest impurity. And then it continues. And it just keeps going as long as you let it go. Yeah, so that's basically how decision trees make or that's how decision trees ask questions and then eventually make predictions, eventually make decisions. And so another really interesting property about decision trees is that they're a greedy algorithm. So if you've taken Comp Sci 465, you should know that you should know what a greedy algorithm is. And if you haven't, a greedy algorithm is an algorithm that makes the locally optimal choice at every step of the algorithm. So I said algorithm a lot right there. So what does that mean? That means that once it makes a decision, there's no backtracking, there's no thinking ahead. It just does the best thing at every step of the way, and it doesn't go back. It basically makes decisions, and it doesn't change its answer. So that might not be the best explanation, but we're actually going to see something that really illustrates what it means to be greedy in this context. And so, all right, so going back to the tree. So this is a tree just like any tree in computer science, or it's a binary tree. So it's got all the same properties, right? It's got a root node, it's got leaf nodes, it's got parents, it's got children, it's got all that stuff. It's got depth, right? So depth is like the number of levels. It might be like the number of levels, like -1 or +1 or something. But depth basically controls how like tall it is, like up and down, right? And so if we go into these parentheses and hit Shift Tab, we can see all the parameters. And so we can see there's some of the ones that I was talking about, right? Like impurity decrease, like you can set the min impurity decrease. Maybe it's not worth asking a question if it's not going to decrease impurity that much. Min impurity split, the number of features it uses at each step. Yeah, like some stuff having to do with like leaf nodes. And then max depth, right? Max depth. So we can set max depth. So max depth equals none. So this is the default. Max depth equals none is the default. So you might be wondering, okay, what does that mean? So if max depth is equal to none, it's just going to keep asking questions until it gets everything right, or until it gets everything as close to being right as it can. So that's what this max depth controls. And so if you set it to none, it's going to create what we've created so far. And so by changing max depth, we can control how many questions the decision tree asks. So if you set it to 1, how many questions is it going to ask? Any ideas? For max depth equals 1. Any ideas how many questions it's going to ask? Oh, One question. Yeah, well, we don't know, right? So we run it. Okay, we see. Yeah, so remember how I said each line is a single question. Here, there's only one line, so it only asks one question. And so let's confirm that, right? So if we check here, we can see, okay, yeah, so it only does ask one question. Okay, cool. So if we set max depth equal to 2, how many questions is it going to ask? Max depth equals 2. So here we saw 1 equals 1 question, 2 equals. Oh, so someone said 4. Ooh, interesting. Any other ideas how many questions it's going to ask? 4. Oh my God, guys are guessing 4. Surprised by that. Okay, so oh, 2. Okay, we got some 2s. Let's see. Oh yeah, okay, we can see it asks 2 questions. Or does it? Wait, let's see. Okay, so we got 1, 2, 3 questions. Ah, if I had taken the average of the guesses, we would have gotten it. But what, right? So why does it ask 3 questions, right? So if we go down here and we run this again. Oh, okay, this makes sense. This is starting to make sense. Wow, this is pretty neat. So here, every node that's not a leaf node is a question, right? These leaf nodes at the bottom are the decisions. And you can see there's 1, 2, 3 questions. So in general, the formula for the number of questions as a function of the max depth, it's going to be 2 to the power of max depth, that quantity minus 1, right? So here it's 2 to the 2 minus 1, which is 3. So that's how we get 3 here. And then that 2 to the power, you get that because it's binary, right? So it's like it doubles every time essentially. All right, so that's that. And so here's another question. If we set max depth equal 3, how many questions is it going to ask? 7. All right, right, yeah, 7 exactly. So when you do 7, we can see, okay, cool. It asks 7 questions, right? 1, 2, 3, 4. It only has 4 questions. Oh my God, how could it do this to me, right? It just betraying me. All right, so let's see. Thought I was right, but I'm not. All right, so here I'm gonna zoom out again. So here, right, there's 1, 2, 3, 4. So I was guessing 7, but it only asked 4 questions. What is the deal with that, right? So let's look at the tree. And when we look at the tree, we can notice some very interesting things. For instance, look at this level right here, right? This guy asks a question, this guy asks a question, this guy asks a question, but this guy stops. He stops early. And why is that? Why would this guy stop early? Well, if you look at what's going on in here, it says value 9, 0. So that means that this node is pure, or that everything it predicts is denied is actually denied. So here basically what's happening is it gets to a point where the node is pure, and so there's no reason to ask questions afterwards. So it stops early right here because it's already perfect for this guy. So right, so my guess was 7. So now we're down to 7 minus 1, which is 6. But we still haven't explained why it doesn't ask 2 more questions. And so the answer to that actually has to do with these nodes right here, this orange guy and this blue guy, right? And so this orange guy, you can notice something really interesting, specifically with the colors or the class, right? So here it asks this question. And so it asks, okay, is exam 1 less than or equal to 50.4? If it's true on the left, it predicts denied. If it's false on the right, it predicts denied. So why would it even ask that question then? Like, what's the point of that? Like, why would it ask a question if it's not going to proceed differently based on the answer to that question? Same with this guy, right? It's blue. If the answer is true, it's blue. If the answer is false, it's also blue. Like, what's the point, right? And so this actually has to do with what I was saying earlier about the criteria being impurity and trying to minimize impurity. So here, this might not make a lot of sense unless you think about it in the context of minimizing impurity. Here we go from an impure node to a node that's pure, right? So this is 26 and 3. This is 18 and 0 and 8 and 3, right? So it goes from impure to pure and impure. So this actually decreases impurity. And same with this guy. Asking this question actually decreases impurity because you get to a node that's pure as well as a node that's impure. So that's why it does that. So this explains why I guess 7 minus 1 minus 2 minus 3, which corresponds to 4, which is the number of questions it asks up top. So this actually does explain it. And further, that formula I gave of 2 to the power max depth minus 1, that is actually an upper bound for the number of questions it can ask. It'll stop early or ask these kind of like ghost questions here. Yeah, so that's pretty interesting. Yeah, all right, someone's gonna ask a question. What is meant by pure node? So pure node, what I mean by that is a node where like everything that's predicted as green is actually green and everything that's predicted as red is actually red. Yeah, so I'm not gonna get into it too much here, but you could just trace down this tree and see like, okay, here, this like this node's gonna correspond to like some area up top. Like for example, it might correspond to this area, like to the left of this vertical line, in which case that would be pure because everything to the left is predicted as denied and is actually denied. All right, so that's the decision tree. No, I'm wondering if I have time to say one last thing. Yeah, all right, I'll say one last thing. So I said that decision trees were greedy. I didn't really, or I explained what greedy meant, but I didn't really explain what it meant in this context. So I'm just going to explain it quickly now. If we say max depth equals none, right, and we look at the tree, we can see the first question it asks is about exam one. It's exam one less than or equal to 56, right? But if we set max depth equal to 1, what's the first question it's going to ask? What is the first question? The first question that it's going to ask is the same question. What is going on? Yeah. So that's what I mean by it being greedy. When I say it's greedy, there's no thinking ahead, right? So if I set the max depth equals to none, I'm saying, okay, you can ask a bunch of questions, but the first question it's going to ask is the same regardless. So that's what I mean by the fact that the decision tree is a greedy algorithm. So learning more about machine learning. Yeah. So there's a CompSci 448, which is I thought it was a really good class. I would recommend that again, CompSci 448 if you're interested in learning more about machine learning. Can you characterize a typical MLSS data science jobs? Yeah, all right, I can talk about that. I'll answer that question at the end actually. I'll get to this last algorithm and then I'll go back to your question. All right, so finally we're going to talk about a neural network. I'm actually going to bump this up back to none to make it look nice. All right, so finally we're going to talk about a neural network. So you've probably heard about neural networks, like even just like in the news or in like popular media. There's a lot of talk about how like, oh, neural networks are like, they try to imitate what the brain does, which is true in some ways. I'd be interested to hear like what an actual like neuroscientist has to say about that. But yeah. So what is a neural network? So a neural network, if you've heard of them before, you've probably seen a diagram kind of like this. And so with this diagram, you can think of every node right here as a single logistic regression classifier, as drawing a single line. And so each of these nodes, they're stacked vertically and they're also stacked horizontally. And this stacking allows them to learn more complex associations or more complex relationships within data. So don't we use neural networks to find patterns for non-correlated data? The data you're using is correlated. For non, yeah. So if I'm understanding your question correctly, you're basically asking like isn't this data like too simple to use a neural network on? Is that correct? If that's correct, we're actually gonna see the answer to that question pretty soon. But yeah, basically, so neural networks, the number of parameters and the structure allows it to learn more complex associations in data. So we're gonna create one right now. In the last like 5 minutes here. So I'm gonna say from, zoom in a little bit, from sklearn dot neural network. Yeah. So that question that was just asked is actually a really good question. And we're basically going to see the answer coming up. So from sklearn.neural network, import MLP classifier. So this MLP classifier, this might sound complicated, but it just stands for multi-layer perceptron. So each circle in the diagram I just showed is called a perceptron. So we're just saying, okay, we just want a bunch of layers of these perceptrons. This is actually one of the most like plain vanilla neural networks. I'm going to say NN equals MLP classifier, throw the parentheses on the end and run it. I'm going to run it in order to, again, get inside these parentheses and check out the parameters. And so one of the parameters you can see is hidden layer sizes, and that controls what the structure of the neural network is going to be. So I'm just going to say hidden layer sizes equals 25, all right? And so make sure to put these parentheses around 25. All right, can't speak about the general case. Deep reinforcement learning. All right, so All right, someone had an answer to that previous question. All right, so NN equals MMP classifier, hidden layer size is 25. And so this basically creates a neural network where you have one hidden layer with 25 nodes. So that's, instead of having this, you only have one hidden layer with 25 nodes. Let's see, question. Historical data. Okay, I'm also going to answer that most recent question at the end here. All right, so NN equals, so we define NN, and so then we do NN.fit, then capital X, lowercase y, again, because X is a matrix, Y is a vector. And finally, we're going to say, we call this decision boundary function on NN. And so you've learned that neural networks are really powerful. They're really useful. They should work really well for a very simple problem like this, right? So we're going to go ahead and run it, and we can see, wow, look at that. Looks great. Looks absolutely amazing. No, this is horrible, right? Like what the heck? I thought neural networks were supposed to be smart, right? So all right, so we're gonna have to debug this, right? And so, all right, yeah. So another answer to one of the previous questions. Okay, so what's the problem with this? Okay, we're gonna have to debug it. So everyone knows that the best way to debug is to change absolutely nothing and just like keep running it and hope to get a different result, right? Okay, so you saw I changed nothing and I ran it again and we got this completely different result. Okay, I did it again. Okay, but at least this time we got a warning. We said max iterations reached and the optimizer hasn't converged yet. So yeah, exactly. Exactly. I just got that. And so it turns out that neural networks actually learn using the same process we talked about earlier, gradient descent. And so here, right, so each step is an iteration in gradient descent. And here it's saying, okay, it's basically telling us we haven't taken enough steps. All right, at least that's reassuring. So we can change that. We can say max iter equals 1,000. So the default is 200, so we bump it up to 1,000. We run it. Okay, we still got horrible results. This is just it's awful, isn't it? Okay, we got like half decent results this time, but it still gave us the same error. So I'm gonna bump it up to 10,000 and see what happens. All right, so we get pretty good results this time. Yeah, all right, and still okay, but still getting bad results sometimes. What's the deal with this? All right, so this last thing, I'll just take a couple more minutes of your time to explain why there's such variability in the results, right? Like why would that be? Like you saw, I wasn't really changing anything with the code except for the max iter, but even when the max iter was constant, we would still get very different results. So why is that? Well, like I mentioned, neural networks learn using gradient descent. And so since neural networks have this more complex structure, the loss function or the cost function is going to be more complicated than something like this. It might look a little more something like something like this, or it's actually going to be higher dimensional. So you're probably not even going to be able to visualize it. But the point is that it's going to be more complicated, and it's there might not be just like one minimum that's the local minimum at every point, right? So like here, if you start out here and you take steps downhill, you could end up at this point. But if you start here and take steps downhill, you could end up at this point, which is very different. So you might be wondering, okay, well then how do you determine where you start? So there are some smart initialization methods, but oftentimes, or I think the scikit-learn method is a random initialization. So you can see that where you start determines where you end, and where you start is randomly initialized. So that means that where you end is in some ways random. And so that basically explains the behavior we're seeing here. There are other things that explain the behavior we're seeing here, such as the fact that we only have 100 data points, and this neural network is super over-parameterized. Like we have like way more parameters than we should for a data set this simple. And the point I'm trying to get at here is that sometimes using a very complex model can actually backfire rather than like saying like, okay, well, using a complex model should work even if it's overkill. So that's basically the point I'm trying to get at here. And also I just think it's fun to like go through and like use neural networks like incorrectly and basically look at all the crazy stuff you can get. Yeah, so let's see more in the chat. All right, cool. Yeah, all right, cool. So yeah, so that's about it for the workshop. So yeah, we talked about some not so spicy classifiers, getting into some much spicier ones. Yeah, so I hope you enjoyed the workshop. I hope you learned a thing or two. I'd be happy to answer some of those other questions now. Yeah, and so if you don't want to stick around, if you want to go do another workshop or something, go ahead. Yeah, I hope you enjoyed the workshop. I hope you learned something. Thank you. All right. All right, thank you all. Um, all right, so Peter's asking, what is a parameter in the context of a neural network? Is that dissimilar to a hyperparameter? So in this workshop, I was maybe I was being a little too loose with my terminology. So parameter, what I mean by parameter is like a weight or a bias in the neural network. Like these guys up here are hyperparameters. Wait, yeah, Peter, are you the one who's pretty knowledgeable? So yeah, that was probably an issue of me misusing my my terminology or being a little too loose with it. All right, let's see. The other questions are. Okay, yeah. I should have been more clear with that, but yeah, since this is introductory, I didn't want to get like too deep into it. All right, cool. So let's see. Wondering if there's online resources. Oh yeah, so in terms of future comp sci classes, I think I mentioned comp sci 448, which I thought was a really good class. I learned a lot from it. I would recommend taking that. Alternatively, you could take the Andrew Ng Coursera class on machine learning. So I took that one summer just for fun to learn more about it. And I would recommend that as well. I can send out the link here also. Yeah. Yeah, all right, let's see. There's some other questions up top. All right, can you characterize a typical ML data science job? Should be using these concepts with big data sets. Yeah, so that question that Guido asked about like a typical ML or data science job. I mean I've only done like data science internships, and there's like a ton of variability in terms of what you would be doing. Many of these concepts are useful, even though you might not need to use them like at this level. Yeah, so and fine-tuning the special cases to determine answers. It's a whole other set of tools or techniques. Yeah, I mean, there's a whole other set of tools and techniques depending on your specific area of interest or expertise, right? Like there's computer vision, there's like natural language processing. Like if you're working at a company, you're going to need the domain knowledge from that specific company. Again, I've only done data science internships, so I'm not the most qualified person to answer that question. It seems like yeah, it seems like Peter answered that question as well. Yeah, I think that's those were all the questions. If you guys have any other questions, I'd be happy to stick around. Or yeah, if you have other workshops or other things for HackPSU to get to, it's totally fine. All right, cool.